Welcome back to Physics 12 to week 3 of magnetism, and today we're going to be talking about moving charges in a magnetic field. So, in the same way that charged particles moving through a wire will experience a force on a magnetic field, so will free moving charged particles. They don't have to be in a wire, obviously, to experience this type of force. And if we want to determine the direction of the force on such a particle, we simply use the same right-hand rule, which from now on I'll just write RHR. So we're going to use the same right-hand rule that we used for current. And so just a quick note, we use right-hand rules for wires when we're talking about conventional current. So remember that conventional current is sort of looking at a circuit and thinking of it as a positive charge that's moving around a circuit, and it goes from positive to negative. And just remember, on a battery or cell, this is a cell here, positive is the longer end of the battery and negative is the shorter end of the battery. If we want to talk about if we want to talk about negative charges, or what we call in a circuit electron flow, so we know that electron flow is maybe a better picture of what's going on in a wire. We know that in real life, it's not that there's protons moving around the circuit. Those are held fixed in place. It's actually electrons that are flowing in a circuit, but the electrons flow from the negative terminal to the positive terminal. But I want you to take a look for yourself. So the same rules apply for the right-hand rule, so as the left-hand rule. So in both cases, your index finger equals movement of charge, which for a wire we just call current, and our three other fingers these are equal to the field lines, the direction the field lines point. And then last but not least, we've got our force, and this is going to be equal or I put that backwards there, but our thumb is showing us the direction of the force on a charged particle. So let's take a look here. Now this question is saying that we have a magnetic field inside this boxed area that is directed into the page. So into the page for a magnetic field, remember we draw that as the circles. Hopefully you remember that. And so one way to remind you of that is that it looks like an arrow that's flying away from you or into the page. So this is the magnetic field in this boxed area here. And so what would be the direction of the force on the segment of wire in the boxed area if we consider conventional current? So try both of these out. Try using your right-hand rule. And so right-hand rule tells us that current, we're talking about conventional current. So current goes from positive terminal to the negative terminal of a battery. And so we use your right hand for that. So figure out the direction of force on this piece of wire. So as the current is flowing through here, what direction is the force going to be? And then you can use your left-hand rule to talk about electron flow. So electrons, you can picture it as electrons moving from negative to positive. So as it moves through the box, you have to figure out what direction they're pointing. Point your index finger with your left hand in that direction. Three other fingers represent the field lines into the page, and your thumb will tell you the force. Pause the video now, see what you get for both answers. Okay, hopefully you have paused it and you've tried this out. So in this case here, for conventional current, we've got positive charges moving this way through the circuit. Positive charges moving that way. So my right hand index finger is going to point in that direction. My field lines are going to be into the page, so my three other fingers are going to be pointing downwards towards my tablet or towards your paper if you're doing this on paper, and my thumb is pointing towards me. So that tells me that my force is downwards when I consider conventional current. Now let's look at electron flow. Electron flow means that we have negatively charged particles moving this way through the circuit. And so I'm going to use my left hand index finger pointing to the right. Again, my three fingers of my field lines are going to be pointing into the page, and my thumb is going to be pointing towards me, or what I would call down in this case. So in both cases, we're going to get the exact same value or direction for force. It's going to be going this way here. So in both cases, it's downwards. And so this tells us that it really doesn't matter if we want to think about conventional current or we want to think about electron flow, you're going to get the same answer regardless. The laws of physics don't really change in that case, so either way, that's going to be fine. So it doesn't matter. And we can use the exact same logic when we're dealing with charged particles. So in this case here, positive particles, we're going to use the right-hand rule. And for negative particles, we're going to use the left-hand rule. Same idea as before. Index finger points the direction of the charges moving. 3 fingers point the direction of the field, magnetic field, and your thumb points the direction of the force on those particles. So this would be, for example, if a question says a proton or a alpha particle. So an alpha particle is 2 protons plus 2 neutrons. These come up in radioactivity a lot. A radioactive particle. I could maybe say that it's a positive ion, etc. So there's lots of different examples of what might come up in a question. For left-hand rule, obviously we're going to have electrons. We're going to have, sometimes electrons are called a beta particle. For some reason, a beta particle isn't just an electron. A beta particle is an electron that comes from the nucleus in radioactive decay. So both of these are radioactive particles. An alpha particle comes from a nucleus, and a beta particle comes from a nucleus. But essentially, an alpha particle is 2 protons, 2 neutrons. An electron is a beta particle. Just it kind of tells you where its origin is for a beta particle. And of course, we could also say this is a negative ion, or a charged particle that's negative, etc. So if we recall, so we're going to try and find a formula here for the force acting on a charged particle. Now, if you remember, the magnitude of a force on a wire was this formula here, F equals Bill. So this was the B field multiplied by current multiplied by the length of the wire that it's acting in this magnetic field. So let's see if we can derive a formula. I would love you to try doing this derivation yourself. For the length here, what I want you to do, if you're going to try this yourself, is think about the motion of the particles in a wire. How far will they move in a given time? So you're going to leave length in terms of 2 other variables. So think about what variables relate length together if we're talking about the motion of a particle. And then lastly, you put all these 3 formulas together to get a new formula for the force on a moving particle. So if you want to give this a try, to do this derivation, a little bit of a challenge, please try that out yourself and and just come back when you're done. So if you have tried this, let's see what we find out. So we're leaving everything here in terms of variables. Now we have one formula for current, which relates to charged particles. We're talking about a moving particle in a magnetic field. And so whenever we're talking about current, we're talking about the rate of flow of charge. So current is just charge divided by time. Okay, so this is how we're going to get from Bill, F equals Bill, to F equals our new formula. Now length, if we think about this, we know that velocity equals length divided by time. And so, or distance divided by time, but we're going to say length. And so in this case here, the length of the wire is just going to be velocity times time. So if we're thinking about current in a wire, we are thinking about some charged particle moving in the wire. So this is my wire. We've got these charged particles. We're thinking of conventional current here, moving in this direction. Well, current tells me how many charges are passing by in a given amount of time. And then the length is just the velocity of the particles multiplied by the time. So if I put all 3 of these together, I have F equals B times I, but I we have Q over T, and we're going to multiply that by the length, which is just going to be V times T. you'll notice that these t's are going to cancel out, and so we're left with our new formula for the force acting on a charged particle in a magnetic field, which is this formula here. So this is our new formula for force acting on a moving charged particle in a magnetic field. And one question for you, please pause the video and I want you to answer this question based on the information here. What is the direction and magnitude of the force acting on this electron? Pause the video, give it a try. All right, if you are back, well, first of all, let's figure out the direction. So in this question here, it is an electron. So this is a negatively charged particle, which means we have to go ahead and use our left-hand rule because it's a negatively charged particle. So in this case here, the electron is shot. Oh, you know what? This question is the same as the question above. So kind of an easy one here, kind of a giveaway. In this case here, I'm going to take my left index finger. I'm going to point that to the right. I'm going to take my 3 other fingers, which represent my magnetic field strength, and I said it's directed into the page. So again, these 3 fingers go down, and so what direction is my thumb pointing? My thumb is pointing down on the page, not into the page, but down on the page. It's going to be pointing towards you if you're looking at your piece of paper, or down, downwards. Now, what's the magnitude? For this, we have to go ahead and use our trusty formula we just derived. F equals B times Q times V. Now the B given here is 0.2 Teslas. So we have 0.2 Teslas multiplied by the charge. If you've forgotten, the charge on an electron is Q electron equals 1.6 times 10 to the negative 19 coulombs. So times 1.6 times 10 to the negative 19. And I'm going to multiply that by V, and the V was 7.2 times 10 to the 7. Times 10 to the 7 meters per second, and this is going to be our value here. So 2.3 times 10 to the negative 12. I'm just going to write this down here. 0.0, 1.6 times 10 to the negative 19 times 7.2 times 10 to the 7. So this gives us 2.3 times 10 to the minus 12. Okay, so one very specific application, one very important historical example of how this was used was with a scientist named JJ Thomson. So in this question here, and for your homework assignment, you're going to be putting your JJ Thomson hats on. You're going to be pretending you're him, and we're going to try and solve the charge to mass ratio of the electron through a series of related experiments. So in this experiment here, JJ Thomson attempted to find out the charge to mass ratio of what he called a cathode ray tube. So, or what he called cathode rays. So this is a cathode ray tube, or a diagram of a cathode ray tube. Essentially what it is you have a power source here, which fires electrons, because there's a positive plate here and a negative plate here. And this causes electrons to fly out of this plate and down this path here. Now, at the time, they didn't know about electrons. At the time, what their knowledge was, or what the prevailing wisdom was that atoms are the smallest particle. Nothing can be divided like an atom. You can't go beyond an atom. That's the smallest unit of mass that there possibly could be. And so, what he discovered, what JJ Thomson discovered, is that not only is there something smaller than an atom, every single atom has this very small particle in it. And he eventually finds out through the experiment that we're going to walk through in a moment that the charge to mass ratio is about 2,000 times greater for an electron than for a proton, or what he would have known as a hydrogen nucleus. So let's think about what that means. If the charge to mass ratio is 2,000 times greater, well, that means one of two things essentially. It either means that electrons have 2,000 times the amount of charge that a proton has, but that doesn't really make sense. If we have these negatively charged particles that are 2,000 times more negatively charged than a proton is, then all matter would be insanely negative, right? So that's just not really a feasible possibility for it to have 2,000 times as much charge. So the only other option really is to look at it and say, well, then if the charge is the same, but the charge to mass ratio is 2,000 times greater, then that must mean that the mass of this tiny particle, which comes out of atoms, must be 2,000 times smaller than the smallest other known thing, which was a hydrogen nucleus, or what we later kind of termed to be a proton. So this is the experiment that led to that overall discovery, that not only are atoms divisible, but every atom has these same types of particles, what he called corpuscles, or what we call electrons. Every single type of mass has electrons in it. They all have the same mass, so it doesn't matter if he made this out of iron or copper or whatever kind of metal he would have had in his laboratory. These electrons, or corpuscles as he called them, were all the exact same. They all had the same mass, they all had the same charge to mass ratio, and they all came from atoms despite different types of materials being used. Every atom seems to have these same tiny corpuscles or electrons inside them. So very, very important discovery. And we're going to go through an example of how he found that. Actually, before I do, I'll give you a little more context. So what he did in this, actually we'll go through another thing. Here we go. First thing he did is he sent a beam of electrons through a cathode ray tube so that two forces were balanced. Now these forces were a force caused by an electric field. So if we have a positive and a negative plate here, this ends up giving us a positive or creates an electric field going this way. And so if it's an electron, we know that electrons move against field lines. So if I put a proton here, a proton would move this way, but that also means an electron's going to move this way. So there's this force acting on these electrons that's going to push them upwards. He also did at the same time was to create a magnetic field. So he created these circular electromagnets here, and he arranged them in such a way so that even though the electric force is going to be upwards, he needed to make a magnetic field that would be downwards to counteract this. So if we use our left-hand rule, what direction would the magnetic field have to be in this area here? So in this circular field area here, there's going to be a magnetic field. Pause the video for a second, see if you can figure out what direction that is going to be. Okay, so if you're just coming back, what we need to think about here is I'm going to use my left-hand rule. It's an electron moving to the right, so my index finger is going to point to the right. And I know my force has to be downwards or towards me as I'm writing on this paper, writing on this tablet. And so my three fingers are going to indicate now the direction of the magnetic field. And we can see that my three fingers in this orientation, where my index finger is to the right and my thumb is towards me, my three other fingers are going to be pointing downwards into the page here. So in this area here, he sets up a magnetic field in this direction here. Okay, so that's the gist of the experiment so far. So he sets them through so that these two forces are balanced. And essentially, I'm going to go through a series of derivations. It's a great idea if you pause the video between and try and figure these out for yourselves. Everything here is going to be left in terms of a series of formulas or just with variables involved. No numbers just yet. When we do the homework for the week, that's going to involve the real numbers. So when these two forces are set up, so he creates a magnetic field of a specific strength, he creates an electric field of a specific strength, and he sets these two forces so that they're going to be balanced. Now, if we want to find out the velocity, we need to think about the fact that these two forces are balanced. Pause the video here, see if you can figure out the formula for velocity. Okay, if you've tried this out here, then we know that our magnetic field is going to equal our electric field. Now this formula is Q times V times B. I'm exaggerating that it's a little v because I don't want you to think it's voltage. Okay, so this QVB, this is going to equal our electric force. And we know our electric force is just Q times E. If we look at our square, here's E, here's F, and these ones have Q, these ones have Q1, Q2. So we have to multiply by E by Q to get our F. You'll notice right away these Q's are going to cancel. So if I want to find out my V is going to be E over B. That is formula number 1 that we're going to use for our subsequent calculations. Okay, step 2. What he then did is he turned off the magnetic field, but he left the electric field on, and he turned off the field, or he tuned the electric field so that the path of the electron, or what he called a corpuscle, was going to go starting in the center here, and then it would just reach the edge of the plate. So if you put the field too strong, it would end up going this way. If you put it too weak, it would end up going this way. So he fine tunes this so that it hits the exact end of the plate. You'll see why he does that in a second. So what I want you to figure out is the time it would take for it to traverse this plate. So to go this distance L, how long is that going to take? So when you give your answer for t, it should just have these 3 variables in it. So pause it again. Remember, you're using the previous formulas for all these different steps. So pause this again and try and find out that formula here. Okay, so we know in general that velocity equals distance over time. Now for distance, I'm going to use L because that's what we're using in this formula here, or in this example here. And so T is going to be L over V, and we know V is E over B, so L divided by E over B, which is the same thing as LB over E. So this is our second formula. So T equals LB over E. Now, the time here is also the time it would take to move the distance S. Now, you'll notice S is kind of half of the distance between the plates. Okay, so this S, because it starts in the midpoint here, that's where he's aiming these to go right in between these 2 plates right in the middle. And so it's going to move this distance S in the Y direction. Now remember that the electric force is only acting in this direction for the moving particle. So this right here is going to be acting like a parabola. So this is just like projectile motion when you're looking from grade 11 at firing a cannonball off a cliff. Projectile motion, the y and the x are independent. So we need to figure out the distance y in terms of QE, the charge of the electron, plus these other 4 variables here. So again, pause the video and try this for yourself. All right, so if you've tried this out, think about this. You're going to have to use one of the big 3 equations. So I gave you the hint there. I said it was projectile motion. So you have to use one of the big 3 equations. Now in this case here, our big 3 equations, we are trying to find out the distance s that it's traveling. And let's think about what we know for our variables. So d, v naught, v, a, and t. And we're trying to solve for s. And we have t. And we also have v naught. What's v naught in the y direction? It is going to be 0. In the y direction, it starts out just moving in the x direction, so there's no y velocity. T, we know this is going to be L, B, O, E. And D, we know this is S. And so there's only one variable left. And I guess the question, maybe it's a better question to ask, what's going to be the acceleration based on the fact that we know the distance. But nonetheless, let's use the formula that relates these 4 quantities together, the d, v naught, a, and t. So this is our formula, we recall. Now v naught is 0, so that's just going to cancel out. Our d we're calling s. This is the half of the distance between the plates. This is going to equal 1/2 at squared. And because we know t is lb over e, this is going to equal to 1/2 a times l squared b squared over e squared. I'm squaring t, and so I'll get l squared b squared over e squared. Now the question here says I want to leave it in terms of q and e and m and b and l. So we don't have q yet in our formula, and we don't have m in our formula here. So how can we relate one of these other quantities? Oh, and our formula still has a, and I didn't ask you to solve it in terms of a. So we need to get rid of our a, and we need to get some q's and some m's in there. Well, how we can take a and turn it basically get rid of our A and get an M in there is to remember Newton's second law. So F equals ma, therefore M equals F, sorry, A equals F over M. So this is going to equal 1/2 F over M times L squared B squared over E squared. And also, the formula here I'm asking for doesn't include F, so we need to get rid of F somehow and also get Q in there. So what do we know for F? Well, we know F equals Q times E. It's the electric force acting on it. And so therefore, I'm just going to put this up to the side. And then so therefore this formula is going to be 1/2 times Q E over M times L squared B squared over E squared. Ooh, are you still with me, hopefully? And so this gives us our final answer here. S equals 1/2 Q over M times L squared B squared over E squared. And so that's that. This is our fourth or our third formula here, this one here. And lastly, what I want you to find out is the charge to mass ratio. Well, look at that, it's right here. So all we have to do now is just rearrange it. So the charge over mass ratio is going to be 2 times S times E, or one of those E's is canceled out from this one here, right? Q times S times E over L squared B squared. I've just rearranged this. I brought the 2 over there, brought the E over there, and brought the L squared B squared down below over here. So here's the interesting part. All of these variables are things that he was able to measure. He knew the distance between the plates. So if we can think of it this way, 2s is equal to 2 times half the distance. If we call this d, then this is just going to be 2 times s. I'm just going to change this d times E over L squared B squared. And E, he would know because E is equal to, if we think back to our square again here, if we have these other quantities here, then V is just going to be, or E is just going to be V divided by distance. So remember, these are over R, these are over R squared. So here we multiply by Q and vice versa, we divide by Q. Here we have field equals potential divided by distance. So again, just a bit of a recap from our previous unit. But E equals V over D. So he would know this value here for E. So he knows D, he knows V, he knows L squared, and he knows B squared. He can measure L, he can measure V, he can measure D, and B he'd be able to measure as well. Remember, he's using a coil, and our formula for the coil is mu naught times I times little n. And remember that little n is equal to the total number of coils divided by the length of the coil. So for example, if I've got 1, 2, 3, 4, I got 7 coils. So this is 7 coils. And let's say this was 1 meter. Then this would be n, little n, equals 7 coils per meter. Okay, or we can just say 7 divided by 1. Same idea here. So this would be a known quantity, one he could calculate. L would be one that he can measure. V would be one that he can measure. D would be one that he can measure. So he had all the information he needed in order to solve this question here. So that's it for the video. But please go ahead and give the homework a try, probably sooner than later while this is all fresh in your memory. You're definitely going to need this information here to give you a helping hand for the assignment. So hopefully you found this somewhat interesting and you learned a bit. All right, thanks again.